Hello students, welcome to my physics class. Myself Dr. Somodipta Pal and I will teach you the classical mechanics. Now when we talk about classical mechanics, this is the mechanics of classical particle, right? Now what is classical particle? So you know that we can divide particles as classical particle and quantum particle. So the particle which have bigger dimension, that is called the classical particle, and the particle which have smaller dimension, that we can tell as quantum particle, right? So that classical particle dimension is such that we can identify that dimension, but the quantum particle dimension is so less that we cannot identify by our naked eye. So the mechanics of those classical particle is called the classical mechanics. Mechanics of quantum particles we call as quantum mechanics. Now in this course I will talk about classical mechanics. Okay. Now we can divide the classical mechanics in two categories. One is Newtonian mechanics and another one is mechanics proposed by Lagrange, Hamilton, D'Alembert, of all those scientists. Right? Now Newtonian mechanics, that you already heard about and you have read this mechanics. So this mechanics is basically describes the Newton's laws of motion, and there are three Newton's laws of motion, as you know. So the first law actually tells about the inertia of the body, means if you don't apply any external force, the state of the body will not change. Means if the particle or body is moving in particular velocity, that will move with that velocity forever. If the particle is in static position, it will be in the static position forever. Right. Now the Newton's second law is telling that the time rate of change of linear momentum is actually giving us the external force applied on the body. So this will give us the measurement of the force, right? And the Newton's third law is telling that if a particle is giving a action force on another particle, so that particle, second particle or second body, will give reaction force on the first particle. So that's why there is a negative sign. So that is the opposite force, opposite reaction force, that you know. Now in the right side, which you see that this is the Lagrangian and Hamiltonian formulation proposed by Lagrange and Hamilton. So why it requires? So in this course I will not discuss this part. Later on I have planned to introduce this thing in my lecture series, so you can find out those portions there, but for the time being only we will discuss about the basics of classical mechanics. Okay. So before going to that, I want to give you some flavor of this, how one can write down the Lagrangian equation or Hamiltonian equation. Okay. So you can see that we are writing L. So this L is called the Lagrangian. So this is a function, you can see, and this function is basically depends on q dot and t. So what is q? So this q is called the generalized coordinate. Now you know coordinate system, right? So x, y, z you tell, that is the Cartesian coordinate. R, theta, phi, that is the spherical polar coordinate, right? Then you can tell rho, z and theta, that is the cylindrical coordinate, right? So this q is somehow related to that Cartesian coordinate or spherical coordinate or cylindrical coordinates. Now why we are telling q, that I want to tell here. So suppose you have one particle So to define the state of that particle, we require the position coordinate, also we require the motional coordinate. So motional coordinate means the momentum, velocity, right? So if the particle is moving, it is changing its position, also the velocity is also important, because it can also change with time, right? So in a single picture, if we want to describe the state of the particle, we require the position, also the momentum. So suppose for a particular particle, only single particle, okay, now you draw a axis in y direction and another axis in x direction, and this x direction axis is actually telling you the position of the particles x, suppose in one dimension we are talking about. So this line is actually represent the x coordinate, and the vertical line is actually telling us the momentum of the particle. So for a particular time of instant, suppose a particle is at x1 and p1 point. So x1 is the position and p1 is the momentum of the particle at that particular time. Then if the time changes, what will happen? The position will change. So x2, and maybe the momentum is p2, momentum is also changing. So we are talking about in general case, right? So here that x1, x2, x3, in this way at different point your particle will move. So here this q is actually represented as x, and this q dot is basically the generalized velocity we can tell, and if we multiply with the mass, it will give us the generalized momentum. Okay, so why it is important here? So when we are considering a single particle, it is easy to handle. Single particle, and it is moving in one dimension. Suppose you have a single particle, only one particle, and it is moving in 3 dimensions. So to define the position and momentum in a single picture, how many parameters we require? So we require x, y and z for corresponding to the positions, and similarly px, py, pz corresponding to the momentum at different directions, right? So for a single particle we require 6 parameters if we don't consider the time for the time being. Okay, so suppose you have n number of particles, so we require 6n number of parameters to define the state of the system, that is the system of particles. And now you think about this. So this is the equation of motion, we know. So to understand the equation of motion of the system of particles or individual particles of the system, we have to write n number of this equation of motion, and we have to solve that to know the state of the system, and that is very much tedious job, right? And there are other drawbacks also I am going to discuss from the next slide. So here this q is basically all those coordinates corresponding to the position, and q dot is the parameters corresponding to the momentum. For the time being, you think like this, and we write down a function which is called the Lagrangian, and that is actually t minus v. So t is the kinetic energy of the system and v is the potential energy of the system. Okay, so t minus v. Now you see here, so this is the Lagrange's equation. Okay, del L del Q minus d dt del L del Q dot equal to 0. Now here this L is only dependent on kinetic energy and potential energy of the system. So you can see there is no force term. So the force is applied on the system, or there are internal force. That's why the system, the particles are moving in some particular way. So here if we measure only the kinetic energy and the potential energy, and if we write down the Lagrangian, and if we solve this equation, we can understand this position. What will be the position means what will be the state of the particle, position and momentum. Okay. Another formulation is the Hamiltonian formulation. There we write down the Hamiltonian in this way. So why this summation is here? Because already I told there is 6n dimensions, 6n parameters are there. So if there are 6n parameters, the summation will be from 1 to 6n, something like this. Okay, so there we define this q dot like this, del I del p, and p dot, that we write del I del q. These are called Hamiltonian's equation. So you will maybe I have planned to discuss this thing in later of this lecture series. So you can find out those. So for the timing I will not discuss in details. So the Hamiltonian is basically T plus V. T is the kinetic energy, V is the potential energy, as I told. And if we add this will give us the Hamiltonian, means this kinetic energy and potential energy, if we add, it will give us the energy of the system. You know that, total energy of the system. So Hamiltonian somehow is related to the total energy of the system. So if we solve this summation qk dot pk minus L, it will give us the total energy of the system, without knowing what are the forces which are applied on the system. That is the important point. We don't know here what type of forces are applied on the system. Only we are measuring the kinetic energy and potential energy. But here the nature of the force, all the force which are applied on the system, that we have to know. Okay. Now let's understand what are the limitations of Newtonian mechanics, which actually insist the scientists to formulate a different type of mechanics. Okay, so basically Newtonian mechanics, you know that it is valid only inertial frames. Now what is inertial frame? You know that the reference frame. So reference frame means to know the state of a particle. To know the state of a particle, we normally construct a coordinate system. That is the reference frame. So there is a origin, with respect to the origin, what is the position of the particle, in that way we write down always, right? So that is the reference frame. So if the reference frame is actually in ideally in static position, static condition, it is not moving, that in that case we can tell this is a inertial frame. Or if there are two reference frame and they are moving in constant velocity with respect to each other, then also we can tell those reference frames are inertial frames. Okay, and non-inertial frames are those reference frames which actually have acceleration. Okay, so Newtonian mechanics is valid only on inertial reference frame. Please remember this. Now as we are talking about reference frame, so there are these are the coordinate system. Already I told they are all normally there are three types of coordinate system: Cartesian coordinate, cylindrical coordinate, and spherical coordinate. So now we will see that if you write down a Newtonian equation of motion in Cartesian coordinate, so what will be the form? What will be the form of that equation of motion in another coordinate system? So there are three already I told. Now that is in 3 dimension. If we talk about 2 dimensional system, we normally consider polar coordinate, that is r and theta. So in 1 dimension, if we write down a equation of motion in this way, so what will be the form in this spherical, in this polar coordinates? So in that case we will write down in this way, m d2r dt2 equal to basically m r d theta dt square. Okay, so here you can see it is not simply like this in this one dimensional motion where we are writing in a simple way. Here we have to consider in this type of equation there is no fr. Okay, so and another problem is here that here you can see here r and theta is actually coupled, they are coupled. Okay, so this type of equation is difficult to solve. Okay, now another problem is, already I told that we have to know all the forces which are applied on the system. Suppose this is a simple example, this is an inclined plane and you put a body. So when you put a body, if you want to write down the equation of motion, you have to consider all the forces which is applied on the body. Now these are the forces which are applied on the body. Okay, so you have to know all the forms of the force, right? Then only we can solve that. So one can easily avoid all these aforementioned difficulties if we use the new formulation that is called the Lagrangian formulation or Hamiltonian formulation. So that I have planned to discuss one of the lecture in my lecture series that I already told. Now let's start with a simple concept, that is the constraint motion in classical mechanics. So constraint motion is basically restricted motion of a body. Now restriction means, suppose a particle you are considering and it can go to minus infinity to plus infinity in x axis, y axis and z axis. So it is free to move anywhere. So that's why it is called the free particle. Okay. Now if I close this particle in this closed box and the dimension of the box is like this, in x axis the length is a, in y axis the length is b and the z axis the length is c. So in that case the constraint of the body or constraint of the particle is actually, the particle is constrained within this length, 0 to a along x axis, 0 to b along y axis, 0 to c along z axis, right? So this is the simple concept of constraint motion. Now let's discuss different examples of constraint motion. So a ball rolling on this horizontal surface, ball rolling on this inclined plane, the ball rolling on the inner surface of the hemispherical bowl, all are the examples of constraint motion. Why? Because if this plane is not here this horizontal surface or inclined plane or this hemispherical bowl, the inner surface of the hemispherical bowl, the particle can go anywhere, but it is constant to move on these surfaces, right? Another example, the oscillation of the pendulum. This bob is actually constant to move in this particular plane in this way. Similarly, the vibration of a body attached to a spring and vibration of molecular bonds in solid materials. Okay, so you know that molecular bonds, in molecular bonds two atoms are connected by bond, simple bond, and that bond we can think about as a spring, and they are vibrating due to thermal agitation, thermal energy. Okay, so how they will vibrate, that will depends upon the strength of the bond, that is basically the spring constant of the spring, right? So these are all the example of constraint motion. Now what is constraint? So constraint is basically that curve or surface on which the particle is actually moving. That means the limitations on motion are called the constraint. So here the limitation is this rectangular box, right? So this is the constraint. Here the horizontal plane is the constraint, here this inclined plane, here this inner surface of the hemispherical bowl is the constraint. Here in this pendulum, this inextensible massless string is basically the constraint, right? And here this spring is basically the constraint. Now what is the constant force? The constant force is basically that force that the constraining object exert on that object which is on that constraint. So the constant force is basically comes due to the weight of the body, the pressure exerted on the constraint, or elastic properties of the constraint. So in this case you can see the particle is moving in this way. So when you hit this normal surface of this box, it is giving a particular force or a pressure. So there will be a normal reaction force on that body due to that wall of the box, right? So that is the constant force. Here the normal reaction force is the constant force. Here also this, when this particle or this ball is moving on this horizontal plane, it is giving a particular force on that horizontal plane. So that horizontal plane will give some reaction force, normal reaction force on that ball. So that is the constant force here. Now in this case also the normal reaction force on that ball. But here it will be simply equal to the weight of the body, that is the mass into the gravitational acceleration. But here in this case we have to consider the components of the weight, components of the weight of the ball. Okay. Here also the normal reaction force by the inner surface of the hemispherical bowl, and in this case the tension in the string is the constant force. Okay. So due to the constant force is basically every motion is happening. In this case the restoring force is the constant force, because due to the restoring force only this body is vibrating in this way, right? So all these forces, due to all these forces, basically this particle is constrained to move. Okay. So this is all about today's class. In the next class we will discuss about constraint equation. What is the importance of the constraint equation? Okay. So thank you for listening this lecture. See you in the next class.